So thank you very much for coming. I'm going to talk about this randomized trial. I've spent 7 years, or actually 10 years, nearly 10 years doing this large randomized trial. And we just got the results just in the summer, and we published the first paper in November or something like that, October or November. And I'm just starting to try and understand the results. Sometimes, you know, I've noticed in previous trials that it takes me quite a while to understand the results. So I'd like your help to understand the results. Because I know there are lots of statisticians in the room, and there's some clinicians. So I'd like to hear your opinions. So please don't be shy. So this big randomized trial, the CRASH-3 trial, follows another trial we did of there's this drug. It was invented in Japan, and it's called tranexamic acid, and it reduces bleeding. You know it as Tranexamic. And we did a big trial called CRASH-2, where we used this drug for people who've been stabbed or shot or in car crashes, and we just in car crashes, and we just, whoa, it's gone. Never mind. That slide shows a reduction in mortality. So this drug really worked, and there was a highly statistically significant reduction in mortality. And most of the reduction in mortality was due to a reduction in death from bleeding. So are you familiar with these kind of pictures? Yeah? The treatment effect in a randomized trial is the relative risk. And this is the relative risk scale on the bottom. This is a relative risk of 1. So if the treatment, and you know, there's no treatment effect, the relative risk is 1. If it's less than 1, it's a benefit. So we found a reduction in the risk of bleeding to death with tranexamic acid, and this very strong time to treatment interaction. So if you give the treatment early, it's much more effective, and if you give it late, it might be harmful. So this was the background to the trial. And so when people have been shot or stabbed, tranexamic acid stops people from bleeding to death. But this man has had a head injury. So his head has been hit by a car, and he's bleeding inside his brain. So this is his CT scan, and this is when he arrived in the hospital. This white stuff here is blood, but it gets bigger. 12 hours later, it's gone from this to this. So he's bleeding inside into his brain, and this bleeding inside into the brain can kill. So we wondered, if tranexamic acid can stop, you know, you bleeding to death from shootings and stuff in the body, perhaps it can also stop you from bleeding into the brain. And bleeding into the brain, head injury is just a huge problem in the world. It's just enormous. There's something like, I don't know, 2 or 3 million deaths every year. So it's an enormous problem, and it's probably about 60 million head injuries, or 60 million, you know, significant head injuries every year. So if we could find a treatment for this, it would be very good. Now, before we did this trial, before we did our trial, there were just 2 small trials. And they were this trial that we did and another trial that they did in Thailand. But they were very small exploratory trials, and you can see they've got very wide confidence intervals. But if you add up the results in a meta-analysis, it suggests quite a large treatment effect. And but we didn't really believe it. You know, meta-analyses of small trials with big treatment effects are not very reliable. Often you get big treatment effects and they disappear when you do a bigger trial. So we wanted to do a bigger trial. So this was the evidence before we did the CRASH 3 trial. And then this is the plan for the CRASH 3 trial. So we wanted to do a very big trial with hundreds and thousands of patients around the world.
So you showed the page, one page before you showed the RR. RR is what? RR is R squared?
It's relative risk.
Relative risk.
Yeah, sorry, it's a relative risk. So, but thank you for interrupting me. So please do that. I hope others will follow your example. The trial was in adults with head injury who were within 3 hours of the injury, because we saw that in the previous trial that within 3 hours of injury. Well, in fact, in this head injury trial, we initially started with 8 hours. Within 8 hours of injury, but we changed it to within 3 hours of injury while the trial was going, because we didn't think late treatment would improve outcome. And they could be randomly allocated, they could be enrolled in the trial if they had a very low level of consciousness as a result of their head injury, because these patients bleed into their brain, or if they had a higher level of consciousness but they had bleeding on the CT scan. And the usual consent procedures, then they were randomly allocated to tranexamic acid or placebo. And we randomly allocated nearly 13,000 patients. 6,000 got tranexamic acid, 6,000 got placebo. And randomized trials.
So how can you do the randomized trial on that brain injury? How to allocate?
How do you allocate?
I mean, for the ethical problem.
Well, in fact, there is no ethical problem, because you don't need to collect written informed consent if it's a medical emergency and the patient is unconscious. So a lot of people believe that you must get written informed consent before you can put somebody in a trial. But there are exceptions. And patients who are in an emergency situation, who are unable to give informed consent, are an exception. In fact, it's an exception that's written in the Declaration of Helsinki. And it's a very important exception. Otherwise, we would never be able to find better treatments for patients in emergency situations. So, we have to do clinical trials for patients with heart attacks and strokes and cardiac arrest, and you can't get informed consent, but you can still do trials because you don't need informed consent. So in this trial, patients would have a head injury. They would come to the emergency department. If there was a relative with the patient, we'd ask the relative for permission. If the relative gave permission, we'd put the patient in the trial. But if they were on their own, which is often the case, if an independent doctor said, yes, it's okay to put the patient in the trial, they could be enrolled in the trial without anybody's consent. And we got permission from ethics committees to do that. So, random allocation of big numbers. So, chance and chance alone determines who goes into the two groups. It's a miracle of science, right? You've got to appreciate this. Random allocation is really, I think, just the most incredible invention. Because the challenge of evaluation is to get two groups that are the same apart from the treatment. And if you can get two groups that are the same apart from the treatment, any difference in outcomes, you can say, is due to the treatment. Yeah? And look, these are the baseline characteristics of the patients in the two groups. And this is the severity of head injury, and it's beautifully matched. 38%, 38%, 33%, 33%, 1%, 1%. It's wonderful, right? So usually when you have a clinical trial, people show this table, baseline characteristics. And people don't pay any attention to it. They just want to get to the results. But I think they're marvelous. I think they're really special because they show the power of randomization, especially with large numbers. Now, we did notice while the trial was going that we were getting, this is called the Glasgow Coma Scale. That's a measure of how unconscious the patient is. And this is a measure of the pupil reactions. Now, the pupils, they react to light, but if the pressure builds up inside the brain, they stop reacting to light. And that means you're almost dead. You're going to, it's a very bad sign. It means that there's pressure building up inside the brain and the brain's been squashed. So we were a little bit surprised that we have so many patients with pupils that weren't reacting anymore, because this means that these patients are almost dead. And if you put patients who are almost dead or in a trial, they can't really benefit from the trial treatment, and they just dilute the treatment effect. So we were surprised by this, and so we planned an analysis that excluded patients who had this very bad prognostic sign. And then other baseline characteristics, everything really beautifully matched. So this is good. This is looking good. We've got, a big randomized trial, 2 groups of patients, well matched at baseline.
How is that this histogram on the GCS? It's almost about the same, but actually in the clinical situation, it's kind of sort of peak on some GCS number.
Yeah.
Is that why do you use that?
This isn't really a histogram. All this is showing is that this is the tranexamic acid group, and this is the percent of patients in these different categories. And this is the placebo group. And what I'm trying to show is that they're very well matched. That's all the only point of this slide. Yeah? At the back with a red.
Question about is there any rule for the doctor to allocate the patient? I mean, you talk about randomly allocate, but we saw this result is also randomly allocate. I mean, but how you tell the doctor to allocate?
How do they do it? Yeah, okay, that's a very good question. So the patient, so we have a box, right? So it's a placebo-controlled trial, right? So in the emergency department, there's a box. And in the box has only got a number on. And in the box, there's either, there are some vials, and they're either drug or placebo. And you can't tell. They're just a clear liquid. And so we have we have a bigger box that contains 8 of these smaller boxes. And so when a patient comes in, you just take the first box. The lower, they're numbered boxes. You take the first box and use that for the next patient. And then the second box for the next patient. So the doctor doesn't know, nobody knows what's in the box until the very end of the trial where we crack the code. Yeah? Does that explain it? We used to use telephone randomization, where you telephone a randomization service, and they'll say, you take some characteristics of the patients, and they say, use box number 44. But what we found that in the emergency situation, doctors didn't want to do that. Sometimes they couldn't get an outside line from the hospital. Sometimes they didn't want to pay the cost of the telephone call. So we made it simpler just by taking the next box, and it works very well. Now, in this randomized trial, so what we do is we have a protocol, and then before we crack the code, we write something called a statistical analysis plan. Yeah? we write a statistical analysis plan saying how we're going to analyze the results before we've seen the data, right? Before we've even unblinded the trial. And so we write a statistical analysis plan and we publish it in a journal. And this is to stop data-dependent analyses. So in a big data set, there are lots of associations, and some of them could be chance, but there's a natural tendency to sort of look for these associations and then find them and lift them up. But we try to avoid that by publishing, by saying, look, this is what we're going to analyze, this is how we're going to analyze it in a statistical analysis plan. And so we said the primary outcome is head injury death within 28 days in patients randomized within 3 hours. And then we added this sensitivity analysis that excluded these patients who we thought were practically dead at hospital arrival. So they were entered into the trial, but we didn't think they had any potential for benefit. And we thought they were almost dead. And because they're almost dead, you know, we'd have preferred they hadn't been randomized, but they had, and so we plan to exclude them afterwards, because if they've got no potential to benefit, they will just bias the treatment effect towards the null. So, was there any question? No.
For the GS3, so then you reject the Tranexamic. You check this.
The question is?
So on that, before the one page before, you showed the patient with the GS number 3.
Yeah. Ah, yes. Yeah, so if they have a GCS of 3, GCS of 3 and pupils that don't react, that's a really bad sign. Those patients, nearly all of them die. And especially in low and middle income countries, nearly all of them die. And so we were concerned that they were randomized into the trial. And so we said that they've got no potential to benefit, or very little potential to benefit. So we're going to do a sensitivity analysis that takes them out and see its effect on the treatment.
So I think just as a question, also that every patient was taken the computer tomography of the brain after and confirm the brain injury then, or just only using neurological.
Just for the inclusion criteria, well, if the patient was very bad, if the patient had a low level of consciousness, they could be included in the trial without a CT scan. But patients who had a more mild head injury needed a CT scan and to see blood on the CT scan before they could go into the trial. Yeah? Masafumi, I think you had a hand up.
Yes, thank you. So, the most severe patients will die anyhow. So, why did you include those patients? Will dilute effect? Yeah,
it was because we didn't expect that they would be included. I mean, when we were planning the trial, some people said, look, we said we should exclude these patients. And other people said, well, sometimes, you can have a very low GCS because you're drunk, extremely drunk. And so we thought, well, let their doctors use their judgment about who to put in the trial and who to not put in the trial. We said in the inclusion criteria that patients should only be randomized if there's a potential to benefit. And we thought that would cause doctors not to put patients with a very low GCS in because they don't have a potential to benefit. But in actual fact, what happens is when you do a trial, people they don't use much judgment at all, and they just put everybody in who meets the inclusion criteria. So, I think the next slide, oh no, I was going to say the next slide as well. So these are this is a histogram showing when patients died. So most patients died on the first day. So 700 and so patients died on the first day. And then, you know, so people die, you know, really quickly. So these are the results. 7 years work, 10 years work, just 2 lines of results. So statisticians in the room, look at those results and tell me what, you know, what do you think? Anybody want to offer an opinion?
So as you said, very low GS number without very very serious about very hemorrhage was not so. But maybe that people who have a head injury, maybe some have a heart attack or like as you can say alcohol or,
Yeah.
or like a benzodiazepine or something like that.
Okay. So let's go through the results. This is the main result, the primary endpoint. So this is the tranexamic acid group. There were 18.5% dead in that group, and there was 19.8% dead in the placebo group, and the relative risk was 0.94, and this is the confidence interval, 0.86 to 1.02. And then in the sensitivity analysis, where we excluded patients that we didn't think had a potential to benefit, we had 12.5% dead in the tranexamic acid group and 14% dead in the placebo group, and a relative risk of 0.89 with a confidence interval of 95% confidence interval of 0.8 to 1.
So that value is between in the 95% confidence interval.
This is the 95% confidence interval here, yeah. So what do you think, you know, how would you describe these results?
No evidence of benefit.
No evidence of benefit. Really? Why do you say that? I'm very interested that you say that.
Is the 95 confidence interval of your primary outcome included 1.2?
Ah, all right. See, I think you're wrong, and but a lot of emergency physicians would do the same thing, right? You take a result, and you immediately divide. The result is just information, and we could with information. Information, I think, is like inherently continuous, right? It's inherently continuous. And there is no, but lots of clinicians chop it in half and actually sort of jump and make this decision. Is it significant or is it not significant? And I think this, my own feeling is that I think that's the wrong way to consider information. But it's exactly what the problem turning out to be. That some people, a lot of clinicians say, the primary endpoint is not significant, and therefore, that's it. We don't need to consider anything further.
And also the issue, you doesn't say anything about tranexamic acid injection. In addition to that, maybe doctor may did some other thing.
So
That every patient will take the CT, GS3. Maybe GS3 in most cases the doctor will take a CT, but
If you had a choice, who would prefer a 12.5% risk of death to a 14% risk of death? How many people would prefer a 12.5% risk of death to a 14% risk of death? Nobody? Maybe I think there must be either you have different value or maybe you're not understanding me. So which is best, a 12.5% risk of death or a 14% risk of death? What, have you got a preference?
I prefer 12.5%.
Yeah, me too. Thank you. So 12.5% is better than 14%, isn't it? Yeah.
I prefer survival without sequelae, not survival alone.
Yes, no, I think that's very important. Yeah, and I have got results about that, and they're coming. But just on the face value of this, so the best estimate of the treatment effect is, let's say this is 0.9 to simplify it. It's a 10% reduction in the risk of death, right? That's the best estimate of the treatment effect, a 10% reduction in the risk of death. But it could be, you know, it could be 20% reduction, or it could be no reduction at all. But no reduction at all, the ends of the confidence intervals are actually, they're not the most probable value. The most probable value is the point estimate. The point estimate is the best estimate of the treatment effect. And it's not the ends of the confidence interval, but it's the point estimate. And you can imagine a sort of probability distribution. So that the most probable estimate is the treatment effect itself, and then it gets slightly less probable as you get. But of course, all results are compatible with the play of chance. And there's nothing special about a 95% confidence interval. You know, we could have a 90% confidence interval, and this would be significant at the 90% confidence interval. We could have a 99% confidence interval or a 99.9% confidence, and it wouldn't be. So this confidence interval, whether it's 90, 99, 95, it's all completely arbitrary, I believe.
Then why did you include GS3 and both unreactive patients?
Why did we
include the GS3 and both unreactive patients? That's his question. Again.
Why did we include them here?
Yeah.
Because we...
that is a primary analysis.
Yeah. You think we should have changed... I don't know. Maybe we should have. Yeah. Why would that made you feel happier?
You insist on the sensitivity analysis result of the.
Okay, we could go for this one as well. We could say that.
But that's only limited efficacy.
It's limited efficacy.
Not so.
Not a big treatment effect.
Not big, not so impressive.
So I think, if GCS is 3,
Yeah.
and also if we see the big hemorrhage in the brain, and also that the position was very fatal area.
Mm.
So we cannot save that patient with tranexamic acid anyway. And then in the case of placebos, in the emergency department, if the doctors see the CT and then the hemorrhage very serious, they just tend to use a placebo, I think. So that then so which means this data says maybe this kind of tendency we can detect, I think. Or it doesn't say anything about other control, if that other think control, properly controlled or not.
All right, so I'm going to keep going. So this is what happened at the editorial stage. So the trial, the paper had gone through peer review, and then 2 editors started talking about the accepted manuscript, and he said, and they were like you, not happy. We'd concluded that tranexamic acid reduces the risk of head injury death, and 2 editors started talking to each other, and they said, well, should it be, can we say it reduces head injury death? And then the senior editor wrote back and you said, you're right. I'll focus on this. You're right to question this. It's only statistically effective in those with mild to moderate head injury. This is really a neutral trial, but is being given a positive spin in the way we don't allow pharma to write. However, this is not pharma and so close to the magical confidence interval of 1. Wow, that's interesting language, right? So this is a senior editor at The Lancet, and they're talking about statistically effective. I don't know what that means, right? I don't know what statistically effective means. I don't know what a neutral trial is. And I don't know what's magical about 1, right? But this is the language that lots of people use. And this is a statistical editor, an editor at The Lancet. So we've really got this thing that it's all about hypothesis tests, isn't it? And it's all about p-values. And it's all about the arbitrary dichotomization of results into being positive or negative based on p is less than or more than 0.05. And I think this is a illness that's common in medicine, and it needs to be cured of it. But
I think pathologically speaking,
yeah.
if the brain hemorrhage is kind of small, the tranexamic acid may prevent worsening of the hemorrhage, because tranexamic acid is the phenylates inhibitor. But if the hemorrhage is too big, so we cannot save anyway with tranexamic acid.
Well, I'm going to come on to that now. But anyway, so I think all of this is very interesting. A neutral trial, you see, the reason he called it neutral is that this view that if the p-value is less than 0.05, it's positive. If the p-value is more than 0.05, it's negative. But if the p-value, as it was in this case, is 0.05, it's considered neutral. So it's not strictly dichotomous. There's a third category called neutral, that if the p-value is 0.05, in this case the p-value was 0.053, right? 0.053. If anybody really believes that 0.053 is materially different from 0.047, for example, I don't understand it. I think this is not the way to deal with medical information, but it's the way we do. And in fact, recently, there was a big piece in Nature about medical scientists rise up against statistical significance. So this was an article that had 800 signatories of leading statisticians calling for a stop to the use of p-value in the conventional dichotomous way to decide whether a result refutes or supports a scientific hypothesis. I'm all for that. And it says, we must learn to embrace uncertainty. So we recommend that authors describe the practical implications of all values inside the confidence interval, especially the observed effect or point estimate. Now that makes sense, right? So what you're saying is like, okay, possibly, it could be that there's a 10% reduction in the risk of head injury death. Now that would be, what are the implications for that? Well, first we've got to know, are there any downsides? Is there more disability? Like Professor Furukawa suggested, could there be side effects, more disability? But if there isn't, then a 10% reduction would be rather nice. And it could even be, and it could even be bigger than that. It could be a 20% reduction, or it could be no reduction at all. So not statistically significant does not mean no effect, but most medical, that's what's claimed in most medical journals. And in fact, there's been a recent statement from the American Statistical Society, American Statistical Association on, so it seems that medical statistics invented this thing, the p-value, and now it's trying to distance itself from it to some extent. Perhaps it's not trying to distance itself, but it's noticed that this concept is being abused. That people are dichotomizing results into positive or negative based on this value. So this is sticking with the primary endpoint. This was the data before the trial. In fact, if you're really interested in statistically significant results, there was one there before we even started. But I didn't believe this big treatment effect. And now these are the trials that have been done afterwards. There was our trial and another reasonably big, not as big as ours, but about 1,000 patients from Washington got the same result. And if you add these two together, but I'm not adding them with this because I don't trust small trials, but if you add these two together, you get that. It's no different. It is actually statistically significant at the less than 0.05 level, but it doesn't make any difference. The results were just the same without it.
So is that, diagnosis guideline is worldwide the same? The GS3 unconscious patient part,
At the moment, these results are just people are trying to figure them out and make guidelines along the way. So that process is ongoing. So, coming back, sorry, Masafumi.
Oh, thank you. I'm very curious about your wording in the conclusion section. You said TXL reduces waiting days.
Reduces
Waiting days. Head injury waiting days.
head injury death.
Yes. So it's very assertive expression. That your primary analysis was not significant, but this meta-analysis was significant. And I'm very curious why Lancet editor permits to use that very assertive expression in the conclusion. Can you understand my question?
Yeah, I can, and it's because I had a big debate with the Lancet about it. I said this dichotomization of results into positive or negative is an abuse of medical statistics. That's what I believe. And I managed to convince the editor of the Lancet that that was the case. The fact that the American Statistical Association agreed with me did help a lot. And the fact that 800 statisticians have written an article in Nature saying that we must stop dividing results into statistically significant, we must stop even using that phrase, right? These two words joined together cause so much damage, and they don't mean anything. That it's an excuse to stop thinking about results. This trial contains information, and information is continuous, and we have to understand it in all its continuousness. We mustn't say this is statistically significant, that's not statistically significant, therefore you can't say it reduces deaths. The reason I think that you can say it reduces deaths is because the best estimate of the treatment effect, which is the point estimate, suggests that it does. And it could be a 10% reduction in the risk of death, it could be a 20% reduction in the risk of death, it could be hardly any reduction in the risk of death. But it's still, the best estimate is that it reduces the risk of death. And we should be allowed to say it irrespective of the statistical, of the p-value, or wherever if p-value is on this side or this side of 0.05. 0.05 is completely arbitrary. Where did it come from? Where did it come from, 0.05? Why is that so important to you? You're blaming Sato Sensei. In fact, hang on. This is quite nice here. This is the way the American Statistical. It says, why do so many colleges and graduate schools teach p is equal to 0.05? And the answer is because that's what the scientific community and journal editors use. Why do so many people still use p? Because that's what they were taught in college or grad school. So it's just part of history, and it just keeps on rolling on because people believe it. People believe it's right, and they do it, and it just carries on. But I think we've just got to get away from it. We've got to. It's not helpful, and I think it's causing more problems because this is so. There's a group in the UK that looks at trial results and makes policy, and the experts on the guidelines committee think it's essentially a negative study. There was no significant improvements. Everybody's doing it, Everybody's doing this negative, positive thing with results. So, right, coming on to your point now, you hypothesized that the treatment would be more effective in patients with less severe injuries. And so that's what we did find. So in patients who had mild to moderate head injury, there was quite a large reduction in the risk of death. But in patients with very severe head injuries, there was very little reduction. There was no reduction at all, in fact, minuscule, tiny, but no evidence of any reduction. So now we're getting more complicated. Now we're having to look at the results and try to think, we're trying to get the meaning out of the results, So in patients with mild to moderate head injury, there was a large reduction in the treatment effect, but not in patients with severe head injury. In patients whose pupils react, there was quite a large reduction in the treatment, in the risk of death, but not in patients whose pupils did not react. So now we've got to think, well, maybe, is this, you made a hypothesis, you thought the treatment, it's a very plausible hypothesis, and there's some evidence here that supports it. But it's more complicated than that, in that in severe, if I go back a slide, patients with severe head injury didn't seem to do very well, but this is not a pre-specified analysis. It's an exploratory analysis. That's why I've got this big warning sign down here. In high-income countries, there was some suggestion that patients with severe head injury did better, but in low and middle-income countries, they didn't. Now, maybe that's a statistical artifact, but maybe it's real. So we have to start thinking about the results, you know. We have to start to think, well, what's going on biologically inside this, you know, in this trial population? So we can see some interesting things here. In low and middle income countries, the death rate is much higher than in high income countries. Yeah? So, you know, there was 37% dead compared to 21% dead. So, you know, many more patients die in low and middle income countries. You know, poor countries, a lot of the patients were recruited in Pakistan. And I've been to hospitals in Pakistan. They're not like hospitals in Japan. They're very simple.
So in this study, brain hemorrhage is only in the inside of the cerebellum, or is there semi?
It could be any
SAH or something like that.
Anywhere.
In the case, in the case of the SAH, open the head bone or some drainage or something like that. But in that kind of things cannot be properly done.
They can do neurosurgery. They do have neurosurgeons, but they don't do very sophisticated neurointensive care. So I'll keep on going. So we thought that the treatment would be most effective when given early. And we saw this very strong time to treatment interaction in patients with mild to moderate head injury. But there was no evidence of any time to treatment interaction in severe head injury because there was no benefit. You know, if there was no benefit, then how soon you give the treatment doesn't really make any difference. But where there is a big benefit, and it's quite big, you know, the earlier treatment is better. So this is this is a sort of something that this is a way to explain a concept, right? And it's about null bias in randomized trials. And I think it's a big problem in head injury in particular. And this is my way of explaining it to clinicians. I know statisticians could get it in a very complicated way, but in a randomized trial, in our big trials, basically, you know, the relative risk is the risk of death in those who get the treatment divided by the risk of death in those who get the placebo. Now, in big trials, you know, if you randomize 20,000 patients, you get the same denominator in both groups. About 10,000 get the treatment and about 10,000 get the placebo. And so you can just sort of cancel out the denominators. Just, you know, to make things simpler, the relative risk is just the ratio of events in the treated group and the untreated group. So if you divide the number of events in the treated group divided by the number of events in the untreated group is the relative risk, because the denominators cancel out.
So what's the relationship with R square and relative risk, mathematically?
I don't know. But I don't want to go into it. It's not a question for me, it's a question for some statisticians afterwards. But the relative risk is the measure of treatment effect in a randomized trial. And it's basically just the ratio of events, right? Now, we've got two different kinds of events here. We've got oranges and apples, right? Now, this is the treatment group up here, and this is the placebo group down here, right? So there's 1, 2, 3, 4, 5, 6 events in the treated group, and 1, 2, 3, 4, 5, 6, 7, 8 events in the untreated group. So there's 6 over 8. That's the relative risk. But there are two kinds of events. There are events that are affected by the trial treatment, and there are events that are not affected by the trial treatment. Yeah? Now, the oranges are affected by the trial treatment. And so the relative risk for this cause of death is 0.5, right? So it's 2 divided by 4 is 0.5, right? The treatment has no effect on this other category of deaths, the apples. And so you say the same number of apples in both groups. So it's just, if you find the cause-specific endpoint, right? So tranexamic acid reduces bleeding. And it reduces bleeding on the day of the injury. So we give a course of tranexamic acid that's only, it's a very short course, it's only 8 hours long, and the drug has a very short half-life, so the drug's completely eliminated after the first day. So there's no drug in the body after the first day. So say this is deaths on the first day due to bleeding, and these are deaths on subsequent days, right? So tranexamic acid reduces, say it reduces these deaths by a half, but has no effect on other deaths. The overall result is really diluted by these deaths that tranexamic acid doesn't have any effect on. Yeah? Do you get that? And the amount of dilution depends on how many of these. So if these apples went on and on and on and on, there'd be lots of dilution. Yeah? So if we have a long line of apples over here, this would get smaller and smaller and smaller, but that would still be there. It's not that the treatment is, it's not that the treatment's not having an effect. The treatment is having an effect, but it's being diluted by this by causes of death that the treatment has no effect on. Yeah? So this is the CRASH 2 trial. This is our previous big trial, 20,000 bleeding trauma patients. What we found is that the bleeding deaths are all on the first day, right? These are days from randomization. So basically, these two are within 24 hours of randomization. So nearly all the bleeding deaths are on the first day. In head injury, you can't say what the patient died of. You can't tell if it's bleeding in the brain or some other thing that killed them. But let's presume that the effect of tranexamic acid is also on the first day. After all, the treatment's only in the body for the first day.
So I think relative risk analysis is kind of a regression analysis, the logit model. Okay.
Right. So this is the effect of tranexamic acid on the first day in the CRASH 2 trial, our previous trial, and the CRASH 3 trial, the head injury trial. Right? So there's a 20% reduction near enough in both. Remarkably homogeneous results, right? So we're seeing exactly the same, I think, biological effect in the CRASH 3 trial as we saw in the CRASH 2 trial. In the CRASH 2 trial, tranexamic acid reduced the risk of dying from bleeding on the first day. In the CRASH 3 trial, tranexamic acid reduced the risk of dying from bleeding on the first day, and by the same amount. This was our hypothesis. So why should the effect of tranexamic acid on bleeding death be any different in head injury? In fact, coming back to this null hypothesis, this p-value thing that everybody's very keen to slice into less than 0.05, more than 0.05. behind any p-value, of course, there's a null hypothesis. You know this. So the null hypothesis is that the treatment, there's no treatment effect. The risk of death in the two groups is the same. But I think we've got to ask, how reasonable is the null hypothesis? Bearing in mind that we know from a big trial of 20,000 patients that tranexamic acid reduces the risk of bleeding on the first day by 20%. See, I believe that the null hypothesis isn't the relevant hypothesis. That actually we shouldn't be comparing tranexamic acid with the null in head injury. We should be seeing, is it meaningfully different from what we found in the previous trial? I mean, they're both trauma trials. So, you know, patients had an injury to the body, patients had an injury to the head. You know, shouldn't the null hypothesis be that, you know, we'd expect similar treatment effects in the two situations? Conceptually, I think it's more sensible to think of the CRASH 3 trial as filling in a missing subgroup of the CRASH 2 trial. So the CRASH 2 trial had 20,000 patients. Some of them had head injuries, some of them didn't have injuries. The only thing they weren't in the trial were patients with isolated head injuries.
CRASH 2 is extracranial, CRASH 3 is intracranial.
CRASH 2, they had to have extracranial bleeding, but some of them also had head injuries. CRASH 3 was only head injuries. So I think these are best seen. This is a trial of tranexamic acid in trauma patients, and this is just a subgroup of this. And so the fact that we get remarkably homogeneous results is that, you know, that's what we should be asking ourselves. Are the results of the CRASH 3 trial meaningfully different, you know, from the results of the previous trial? So this is the effect on all-cause mortality within 24 hours of injury. So tranexamic acid reduces the risk of dying on the first day. But when you get to 28 days, a lot of that treatment benefit has been diluted out by causes that tranexamic acid cannot affect. So tranexamic acid affects bleeding on the first day, but it doesn't have an effect on pneumonia on day 15, or, you know, or sepsis, you know, severe sepsis on day 20. You know, it can't do anything about that.
So this CRASH 2 is a subdivided group into subarachnoid hemorrhage and also the other hemorrhage of extracranial.
Our primary outcome was whether patients died of their head injuries. But the thing about head injuries is that when someone who has a head injury and dies, people just say they died of their head injury. But, you know, they may have died on the first day from raised intracranial pressure, from bleeding, or they could have died on day 28 from a pneumonia. So the effect, so these are deaths on the first day in extracranial injury. These are deaths on the first day in intracranial injury. And we got exactly the same effect on deaths on the first day, the bleeding deaths. And what we got is dilution towards the null by the apples. But because we have more apples in patients with head injury, we get more dilution towards the null. And in patients with mild to moderate head injury, you don't get so much dilution towards the null. So this is mild to moderate. So severe head injuries, you know, they're very high death rates. So you get this early treatment benefits completely diluted out by late deaths. But in mild head injury, it's not, because if you don't die of bleeding on day one, you don't die of anything else. But with severe head injury, if you don't die of bleeding on day one, you only live to die from something else the next day or the day after that.
Yes, I agree with you that these results are very consistent in class 3 trial and among other trial in class 2 and class 3. Yes, I agree with that. That these are all subgroup analysis. And we are taught from Sato sensei and Fuka sensei that the results of subgroup analysis are just hypothesis generating, especially when the primary analysis is not significant. So can you say the results of these subgroup analysis are conclusive or just generating?
I don't know. I think I think when you've got a body of results, what you try and do is try and understand. It's a sort of collection of information, and you try your best to understand it. That's how I approach it. And it's this thing about, I understand the need to avoid data-dependent analyses, and but there is important biological information in subgroup analyses as well, I think. And I think we want to learn from that.
Yeah.
I think you have to distinguish between the conclusion to be drawn from this single trial and also how to interpret the findings. And then the conclusion to be drawn from this single trial should follow at least the rules of the randomized controlled trial, which says unless you have p less than 0.05 for your predefined primary outcome, the trial is essentially negative. However, you can interpret that along with other evidence. And that is exactly what you are doing.
But where did this rule for randomized trials come from?
Well, FDA.
FDA.
Yep.
Is that true?
Well, originally from Fisher.
But did Fisher say less than 0.05 the treatment works and more than 0.05 the treatment doesn't work?
No, he didn't say that. He said that unless, well, let's forget about this 0.05 because I do essentially agree with this artificial dichotomization at 0.05, and I am basically for ditching out p values. However, the interpretation of a statistical trial should be guarded because in order to guard against inflated alpha values, that is the lessons we have learned through the history of conducted and misinterpreted clinical trials. But having said that, what you are trying to do with this subgroup analysis is, I think, essentially prediction model. You are saying that looking at the bigger picture can be diluted by some other insensitive groups. So you want to pick up sensitive groups which do respond, in this case, to taxanemic acid. And that is a prediction, subgroup analysis, and building a prediction model to run or to do stratified analysis. But the caveat there is that overfitting. Therefore, I think what you are trying to do should follow the rules of the building of the prediction models, in which you first build your model on the training set, and then try to validate that in an external sample. And if that prediction model, meaning that this works for this subgroup but not for that subgroup, is validated in an external.
I don't know whether I don't see where the prediction model is though in here. I feel it's just like you've got this collection of information, you've got this data, and you're trying to use your biological knowledge and your statistical knowledge to understand what's happening.
Well, that does not serve the clinical practices, because we want to know if the results apply to your next patients. And in order for the results or your biological understanding to be applicable to your next patient, you have to validate your prediction model or your subgroup analysis.
Oh, okay. All right. So, more results, no increase. I mean, we're worried about, obviously you're worried about if the treatment improves outcome. If the treatment reduces the risk of dying, perhaps it increases the risk of disability. Well, it didn't. There's no evidence of an increase in disability in the survivors. And no evidence of disability in the survivors again. And then you might be worried about side effects, and there aren't any side effects. Whether you give it, whenever you give the treatment, there was no increase in any of the side effects that we collected. So you might think, well, treatment reduces bleeding, might increase the risk of vascular occlusive events, but it didn't. So the risk of so now we've got a situation. We've got a treatment. It's an inexpensive treatment. It seems safe. Japanese women take it every day to whiten their skin. I don't know if you know this, but a lot of Japanese women like to have skin that looks like mine. And they take tranexamic acid. One of its side effects, one of its few side effects, is that it tends to whiten the skin. And so lots of Japanese women take a gram of 750 milligrams of tranexamic acid every day for this purpose. It's sold over the counter in Japan as a beauty product. But anyway, that's not science, that's just an anecdote.
I have a question as a clinician. Pulmonary embolism is really underdiagnosed in Japan.
Yeah.
But in this study, how is kind of
How
sensitivity, general sensitivity to detect pulmonary embolism?
Well, what we try and do in clinical trials is not have very sensitive diagnosis, but we have very specific diagnosis. So we only want people to record a pulmonary embolism if they're sure it is. Now the reason we do that is that if you have high specificity, there's no bias. I mean, you might miss some cases, but the danger is of including cases, calling something a pulmonary embolism that's not a pulmonary embolism. And so we avoid that by having high specificity. And so but we don't find much evidence, we don't find any evidence here that tranexamic acid increases the risk of pulmonary embolism. So, I was saying, we've got a treatment that's very cheap. It doesn't seem to have any side effects.
And also the stroke, they don't say stroke is including infarction and also hemorrhage.
Yeah, this is clinical stroke. Yeah. So it's an inexpensive treatment. It doesn't increase the risk of, it doesn't seem to have any obvious side effects. It reduces the risk of death by about 10%, but it could be much more. Could be as much as 20% reduction in the risk of death, or there could be very little reduction in the risk of death. But the best estimate is a 10% reduction in the risk of death. I think, well, why wouldn't you want this treatment? Why wouldn't you want it? So, okay, there's a risk, and there's always a risk that it's a false positive, right? That you've falsely concluded that the treatment's effective when it's not. Now, there's always the risk, but you might say, okay, the risk here, if you falsely conclude the treatment is effective, then you've given someone a cheap treatment with no obvious side effects. If you falsely conclude that the treatment is not effective, then you've denied somebody a 10% risk, 10% reduction in the risk of death. I think, okay, now I have to weigh all of these things together. Which is worse? I know what I would want. If a relative of mine had a head injury, I would want them to get tranexamic acid as soon as possible, preferably at the scene of the injury. That's what I would want, because I was talking to neurosurgeons about this, and they were saying, yeah, but they were going this 0.05 thing, and I said, well, look, they open people's head up, they drill holes in people's head and take blood out. And I said, is there any evidence for randomized trials for that? No. So there's no evidence for any of the things that most doctors do to patients. And here we've got, I think we've got so much more evidence. So this is the results of the CRASH 2 and the CRASH 3 trial on head injury death within the first 24 hours. And low and middle income countries, you get slightly, people often say to me, because we do global trials, they say, oh, you're doing them in poor countries. Well, those don't apply to wealthy countries like United States and Japan, but they do apply. In fact, the treatment effects in high income countries are slightly bigger. It's not statistically significantly heterogeneous, but it's about the same. So I think we've concluded, I believe that tranexamic acid is safe in head injury patients, that it reduces head injury deaths, but that the statistical teaching has damaged science because we have stopped thinking and it's much easier to dichotomize than to think. It's much easier to have a decision rule than to use our judgment.
I have a question.
Yeah.
So, when you wrote the statistical analysis, so did you describe the statistical significance as in 5 p-value of 5% or 95% confidence interval in your sub, or so? We did not mention p-values at all in the statistical analysis plan, apart from heterogeneity p-values. It's the only p-value that I find acceptable is a heterogeneity p-value. So we only talked about heterogeneity p-values. We didn't talk about p-values at all. So there's no mention of p-values in our statistical analysis plan. We said we would present relative risks and 95% confidence intervals. But that doesn't mean to say, we're not inviting you to turn it into a p-value. We're not, like when you have a confidence interval and you look at it and you say, aha, the upper bound of the p-value of the confidence interval includes 1. All you're doing in your head is you're turning a confidence interval which is telling you lots more information. You're turning it into a p-value. And you're doing the dichotomization of positive and negative, less than 0.05, more than 0.05. So in our statistical analysis plan, we didn't mention p-values, but we talked about 95% confidence intervals. Does that answer your question? Do you feel happier or less happy or?
First of all, I like how you fiercely defend your data, because I work in immunology and genetics, and honestly, the last thing I look at is the p-value. I try to look at every single piece of my data before But what if in the side effects you notice that it is idiosyncrasy of tranexamic acid?
So what if, I couldn't hear that.
An idiosyncrasy to the tranexamic acid, and you are not supported by the p value now. So would you, like, now the physician will be afraid my patient might die, but I have no parameter to estimate if he's going to that allergic reaction. But what if I am conducting a trial and I'm now in your position, but my drug is inexpensive but has a serious side effect? Should I go to the public and say, just give it a try, or should I just know it's a negative conclusion?
No, I think if you've got a side effects, that if you've got a significant side, a meaningful, significant to the patient, not statistically significant, if you've got evidence of a side effect, then you have to start weighing off things. You have to say, on the one hand, I've got this potential benefit, on the other hand, I've got this risk, and then you have to make judgments about, the values of the, the risks of the different things and the utilities of the different things. But in this case,
Parameters you should suggest, like, because we invent the parameters and values to help us judge. So now we are like given up on p-value. So you suggest like relying on other parameters? Or just considering it if it's the only way to judge?
the American Statistical Association, I don't think they said stop using p-values. But they said stop dichotomizing on the basis of them, right? Because this p is less, stop saying that results are meaningful or not meaningful depending on this arbitrary value, this arbitrary dichotomization. That doesn't make any sense at all. The null hypothesis, the p-value is the probability that if the null hypothesis is true, that you'd get a result as extreme or more extreme as this by chance alone. Now where does, and that's a number that goes anything from 1 to 0, but where does this 5% come from? It's not helpful, I don't think. And so results should not be dichotomized into positive or negative. They should be seen within the broader context of what's gone before, other trials in the area, biological insight. It all has to be brought together. And so So I think statistical teaching, I think we have to learn to embrace uncertainty, and we have to weigh off the different, we have to think, well, let's see, what are the consequences given the point estimate? What are the consequences given, a smaller treatment effect or a larger treatment effect? What are the implications? We have to make our judgments about that. But we have to make judgments. And I think dichotomization is a problem.
Yeah, it should be that the bad statistical teaching has damaged science.
Bad statistical teaching. Fair enough.
I have a question about
Yeah.
your interpretation.
Yeah.
Because the tranexamic acid reduces the mortality within 24 hours, and then it's effective to the mild to moderate TBI patients.
Yeah.
I think the mild to moderate patient will live long, not death within 24 hours.
Yeah. What?
Can I explain?
Okay. So what happens is that if you have a severe head injury, this is what I think is happening biologically. If you have a severe head injury, your bleeding in the brain can kill you on the day one. If you get tranexamic acid, it's less likely to kill you on day one. So you're more likely to survive. If you have a mild, moderate, or severe head injury, you're more likely to survive, to be alive to day 2 if you get tranexamic acid. But with any treatment, we only live to die from something else. No treatment reduces mortality, it only delays mortality because everybody dies in the end. So with tranexamic acid, you don't die on the first day. That's good. But you might die on the second, third, fourth, or fifth day. If you have a very severe head injury, you get a treatment benefit on the first day. You're more likely to survive the first day, but that doesn't necessarily mean you get out of hospital. There's a big effect on whether you get out of hospital alive. But if you have a mild or moderate head injury, if you don't die on the first day, you've got a really good chance because nothing else is going to kill you. So I feel biologically that tranexamic acid probably has the same effect in everybody. And for that reason, I would give it to everybody. Because getting a patient to survive the first day, why wouldn't I do that, I feel it's just, it's effective in everybody on the first day, but it's all diluted out. And it's, in high-income countries, you get that benefit from the first day, and it keeps the benefit because your chances of dying from something else are less. But in low-income countries, that if you have a severe head injury, you might get a treatment effect on the first day, but you're not going to get out of hospital alive because there are so many other things that are going to kill you. That's my interpretation of the results. But yeah, the lady at the back, I don't feel like I'm defending my data. I don't believe that it is a matter of defense. I'm trying to understand it. But if I really believed the treatment was absolutely useless or dangerous, that's what I would be telling you. I've got no stake in this treatment being effective or good.
But also so many good projects and papers just thrown out because they have no p-value.
Because they don't have a p-value that's less than 0.05.
Yeah, so I made the article since it's really amazing why it's thrown in that place because I think the author, I think the editor, I think the reviewer underestimated their work just because of p-value. But I respect the data that it's giving. That's what I'm saying.
Well, I taught a course on research integrity here last year and the year before, and I met PhD students who were devastated that they didn't have what they believed statistically significant result in their PhD because how and now are they going to get it published? And if they didn't feel they could get their PhD paper published, they didn't think they would get their PhD. And they were searching around in their data for something that was significant at the 0.05 level. And it's really bad for science.
And that's what I'm saying, because they gave up. They didn't try to make their data meaningful, even if the other p-value is not supporting them.
Yeah, I think sometimes they imagine what editors think more than what editors really think. And they get this focus on a p-value, and that leads to this sort of p-hacking, where you're searching around for a significant for a less than 0.05, and then you exclude a few patients here and a few patients there, and you get the right result.
And sometimes you see the opposite. Sometimes you get the good data with the very significant p-value, but from a biological point of view, and make the context unfair.
Yeah, I think it degrades our thinking, and it's really bad for science, I think, that we dichotomize in this way. And that the editor of The Lancet does too, It's a neutral result, quite close to the magical number of 1. I mean, I don't know what they're talking about. But the good thing about the editor of the Lancet was that I spoke to him on the phone about it, and he was convinced. You know, he changed his mind. So, you know, I think it's good from that point of view.
Yeah. So may I ask how many rounds of exchanges you had with the editors at the Lancet?
Well, it was all going very well. They sent the paper out for peer review. The paper was accepted. And it was just at the copy editing stages where there was this interchange between two editors, copy editors. And one said, oh, should we say this because P is not more, you know, the confidence interval includes 1. Should we say this? And then the other editor said, maybe not. We'd said, tranexamic acid reduces head injury deaths. And there were 3 rounds of proofs because we want to get it all correct. The first round, the second round. In the third round, they added a word. And it said, we'd written, tranexamic acid reduces head injury deaths. And they'd add this word, might. Tranexamic acid might reduce head injury deaths. You know, it's like a tabun, you know. I mean, we knew that before we did the trial. So, like, I strongly objected to the inclusion of the word might, because I thought, well, crumbs, don't give me might. I knew that, but, you know, you could say that before we randomized 12,000 patients, that it might reduce head injury deaths.
But then did no reviewer point that out?
No, and I think it's a credit to them because I think it's because they were more clinical, actually, that they actually saw the results more as in the gestalt, really. All right, you know, it reduces, you know, there's evidence of treatment effect in the mild to moderate, as we'd expect. We wouldn't expect much of a treatment effect in the severe head injuries because they have, you know, lots of intracranial bleeding at baseline. You know, you might say it's a subgroup analysis, our mild to moderate head injury, but it was a subgroup analysis that had, I don't know, 6,500 patients in. You know, it wasn't like, it wasn't a trivial subgroup analysis. So nobody objected, no. And the other thing I pointed out is the that we ought to sort of look at the results in a more Bayesian way, really. That we ought to take into account what we already know about this treatment. And maybe the null hypothesis isn't the right reference point.
I think there you're going beyond the single trial and going into meta-analysis and evidence synthesis.
No, I don't think so. I think it's a sort of, you know, taking into account what we already know. You know, it's like what is your sort of, it's like having a prior, you know. Well, in tranexamic acid reduces bleeding in surgery. It reduces extracranial hemorrhage. Most of the treatment effect is on the first day. And then we find in head injury patients, tranexamic acid reduces bleeding on the reduces head injury death on the first day. Yeah, how do you put all of that together? You know, well, the p less than or more than 0.05 doesn't even come into it. You just now you have to start thinking about, you know, biology, and that's, you know, that's what we should be thinking about, I think. Yeah.
I have a comment. In fact, the last time I listened to a seminar about the immunotherapy, that about the statistics, because they have they give a figure about the treatment and placebo. At the first 3 months, they coincide with each other, but from the 3rd month to the 9th month, the treatment showed a better effect. And after that, the 2 curves after 9 months, it almost stable like that. So they talk about the lifetime, the delay I'm just wonder that in this case, of course, how can I say, the improvement of the statistics should to let us to want to choose as closely as possible. So in this case, I'm also wondering, how can I say, is there any delayed effect to the patient? For example, if this patient can survive until the second day, maybe this treatment will show effect to those kind of patients. I was wondering about such kind of effect.
Yeah. I think with the cancer example, when there was no benefit and then it appeared later on, I think you just have to interpret clinical trial results in the light of what we know about the biology of the drug, how it works. But in this case, I think living, surviving the day of the injury, I don't know why we wouldn't offer that to a patient, even though they might only die from something else. I don't know why and that was all pre-specified in the statistical analysis plan. We said the effect of tranexamic acid is predominantly on bleeding deaths. The bleeding deaths are early deaths, so we're going to look at the effect of tranexamic acid on, this is our first secondary endpoint. We're going to look at the effect of tranexamic acid on deaths within the first 24 hours. And it was exactly, it was pre-specified, it was not, speculative after the fact stuff. We found, and so if you can get the patient through the first 24 hours, well, it sort of doesn't, this is what, so supposing the late deaths are from pneumonia, right? And we haven't got good treatments for pneumonia. So if the late deaths are for pneumonia, and the lack of an effective treatment for pneumonia seems to be affecting the efficacy of tranexamic acid. So it doesn't really make sense, does it? That tranexamic acid is effective if we've got a good treatment for pneumonia, but not effective if we don't have a good treatment for pneumonia. I think you've got to isolate, you've got to go for the biological effect that you think's important. And not dying on the first day of the injury is better than dying on the day of the injury. And then we'll have to see, well, is there anything else we can do to stop them dying on the third and fourth and fifth and sixth day? But it's an interpretation. I think unless anybody, any more questions or comments or, yeah, please.
Thank you for this presentation. I'm basically emergency physician,
Yeah.
so I understand the result.
Yeah.
I think it is very reasonable. So can I ask, so this, I think this primary analysis and the result means the tranexamic acid cannot reduce the mortality in all head injury, right? And it might reduce moderate to minor head injury. So you say so the result, so estimation is like a continuous variable, so it is not dichotomous. So I totally agree with it. However, the clinical trial is so answer the it cannot reduce all head injury. Is it
Well, I think that's the question. I mean, that's the practical question is, who do you give it to? Do you give it to all head injuries as soon as possible, or do you only give it to the mild and moderate patients?
Usually, so I give all the patients.
Yeah, I would do the same, because I think it reduces the risk of dying on the day of the injury in everybody. But, and those are the oranges, right? There's a treatment effect on the first day, and it's probably for everybody. But it's if you have really bad head injury, you're going to die. You've got a really high chance of dying from something else. But still, it doesn't mean to say that this isn't worthwhile. You know, not dying on the day of the injury is good. You know, but you only live to die from something else, and that's bad. But you know, you would give the patient the mechanistic benefit that you feel. That's how I interpret the results. In fact, clinicians are much more naturally intuitive in statistics, I think, so in that sense. You know, it's almost like a little knowledge is a dangerous thing, but you know, yeah. I agree with your interpretation.
Yeah, I totally agree with the understanding. So the result is continuous, so not dichotomous. Because I am an emergency patient, so I every day see the patient. So it's like a gray scale, and the result is not 1 point. So yeah, your presentation is very interesting, and the discussion is very interesting to me. So it's very learning.
Yeah, I think at the moment what's happening is that lots of different people in lots of different places are looking at the results and trying to make, okay, what does this mean? And different people are coming up with different you know, interpretations, and that's very natural. You know, yeah.
Do you expect your results to change the guidelines for management of head injury?
Yeah, I mean, I think they will. They are doing so in the UK. People are not, I mean, there was some conversation with guideline people saying that the results, one of the people said that, you know, this is a negative trial, and then I sort of objected to that use of language, but I mean, there's guidelines processes, and then there's clinicians themselves, and you know what, they're related to each other, but clinicians can do what they. I mean, I've had lots. Yeah, different people will be doing different things. But what I would like them to do is try and look at them all, take everything they know about the treatment and the condition, and try and, you know, synthesize it all, and not sort of just dismiss it quickly. You know, I think it's a lot of information. It's the biggest head injury trial ever conducted, and if we just sort of throw it away on the basis of the p-value for the primary endpoint, that would be a big waste, I think. More questions? No. In that case, thank you very much for sharing.